Hello and welcome everyone. So I'll be explaining recent Codeforces round 716 div 2 problem B. Quite interesting problem. So this problem actually involves both bitwise concept and binary exponentiation, also a bit of combinatorics. So let's jump into it. So in this problem, basically you're given two integers n and k. You have to find out the count of the number of arrays of length n. Okay, we define n as the length of an array, and you have to find how many of an array you can create. But there is a condition. What are the conditions in order to make that count of arrays? There are possibly three conditions here that they have given. These three conditions are that all of its elements inside that array, the integers will be in between from 0 and 2 to the power k minus 1. Now this information is quite interesting, and it is important to learn about this part here, because all of its elements are integers in between 0 and 2 to the power k minus 1. I'll explain it how. So this was the first condition that we need to fulfill. Each and every element could be between from 0 to 2 to the power k minus 1. Also, the bitwise AND of all of its element, ultimate result should be 0, or must be 0, and then the sum of its elements itself is as large as possible. So admitting and enabling these three conditions, you have to measure how many of the same type of operations that you're going to be making, and fulfilling these three conditions, how many arrays that you're going to count, or how many arrays that you can create. That's where the combinatoric part comes. So before diving into the solution, we need to understand one thing here. Let's say n and k, we're given n and k, and we know that the integers are going to be from 0 till 2 to the power k minus 1. Now, what is this actually referring to? 2 to the power k minus 1. If I write down any integer's binary number, which is referred to as 2 to the power k minus 1. If you could understand that, let me explain you. 2 to the power k, let's say this number, any number which is 2 to the power k is a non-negative integer, assume that this number's binary representation is going to have k plus 1 bit, and it will look something like this. The first bit will be 1 and the rest of them would be 0. Okay, total of k plus 1 bits, and also 2 to the power k minus 1. Now this number's bit, it will consist of total k bits, and each and every value of that bit would be 1. So let's say k is equal to 5. If k is equal to 5, then 2 to the power 5 minus 1 would consist of 5 bits of 1 if you denote it as a binary number. Okay, I hope you get that. Now, if we could analyze it, now one of the conditions that they have told us is that we need to make sure the sum of the array is as maximum as possible, right? So I know that, okay, if this is my final, or this is the last value that I can input as an element, so I would definitely want to take that as an advantage, because I know that this number is the largest one, and I better take the largest one rather than the smallest one, because I have to make the sum of the total elements as large as possible. Also, maintaining another condition, which is the AND value of every element should be 0, which means I could model a generalizing array which could look something like this that I've drawn here previously, okay, which could have something like this, some format. I could give it like this. I could give it something like one of the elements would be 0 because I need to AND it, and each and every element, so one of them needs to be 0. I could have an intuition like that. And for the rest of the values, let's take the maximum one, because we have to make the sum as larger as possible. And that's pretty much it, fulfilling all these three conditions. So all these three conditions, we have figured out how we're going to be inputting. So the value that matters is actually 0 and to the power k minus 1 is going to be the members in our array. Now, so far we have actually modeled the array, but what about the real thing? The real thing is that we have to count how many of these arrays that we can create. That's when the question comes of combinatorics. And let me tell you what will be the answer. The answer will be n to the power k mod the mod value. Now, why is that? In a combinatoric sense, the answer would be n to the power k, but the explanation is what I'm here for. Why the answer is n to the power k? How can I say that? Now, interestingly, if you see that, okay, how can we manipulate this form of, or this is generalizing this form of arrays? Remember, this is the first value, this is the second, this is the third, this is the fourth. Okay, I've taken 4 values like that. Okay, now how can we permute each and these sort of bits? Now, if you think about it, a bit from the 0 members, from the character 0 perspective, then it would seem pretty much easier, because if you look for this bit, only this 0, okay, I'm not considering the rest of the 1, because the rest of the values are all 1. So let's just consider for the element which does consist of all elements, all bits equal to 0. Now, if I say that I will replace this bit 0 with any of these numbers, 1 bit, just replacing, what's gonna happen actually? Just imagine and just analyze it, and you will see that there's actually no freaking difference. Just no difference. If you AND this, it will give the result as 0. If you OR this value, it will give the same result as the previous one, right? Similarly, if you following that operation, if you similarly do, okay, let's replace this 0 with this one, second value is 1 bit, what's gonna happen? This becomes 0, this becomes 1. Now let's try to make follow those conditions and see what we have here. Then we will see that the result actually, it fulfills every condition possible. So I hope you're getting everything here. Now, that's how we can make and permute each those bits, those 0 bits. Now, what will be the case when it's not gonna be the case? Now, if you see, or if you do something like that, if you make this 0, and if you replace this 0 with this one, then the problem occurs. If you replace this 0 with this 1, and if you replace that, then this becomes 0 and this becomes 1. Okay, so now what happens is from one group of bit goes to another group of bit and replacing their own spaces. I could say something like that. So we have to stick to the positions of the bits, and sticking to the position we will permute. I hope you get that. What I'm trying to say is okay, let's have a fresh start here. What I'm trying to say is basically we will deal with each and every zeros. For each and every zero, this bit will never go to this area apart from its position. Okay, it will never go any other area apart from its position. Okay, so for this 0 bit, its position is sticking here, and it's gonna be inside this area, and it's gonna permute inside this area. So the problem boils down to this positional portion of the bit. Now this 0 has so if I now look down for it and give it a bit of analyzing thought, I will see that this 0, I can replace this 0 here, which is the first value, or here, which is the second value of the first position, or here, or here. So I have like what, total of n possible ways where if I stick to my position and I have n possible elements, that's that positional bit, if I can replace that and I can make another a format of array without restricting or without colliding any kind of conditional problem. Okay, so I hope you get that here. So this 0 is going to be replaced only sticking to its own group, but replacing each and every can be, it has the ability to move forward for each and every positional period of, so a positional period, that would be total count of 1 because there are n elements, so it will stick to its own position of n elements. Similarly for each and every 0 bit. Okay, so now the question comes, how many 0 bits are there? Basically, you know, or we know, we're taking an input extra, which is k, and I've told you that 2 to the power k minus 1 consists of k bits, which means there's gonna be k0. Of course, that's absolutely sure. We're absolutely sure about that. Now, what actually the problem actually boils down to, I have n spaces to cover for each and every 0, but the bits are total of k, so n to the power of k is my final answer. I hope you get that. It's just the basic combinatorics, and I hope you get that why it's n to the power k now. Okay, I hope you get that why it's n to the power k now, not n times k or n plus k. It's n to the power k because for each and every positional situation, the other part of it will have its own permutation. It's pretty intuitive. I hope you get that why it's n to the power k. Okay. Okay. Now the question comes, how are we going to be calculating n to the power k? Because these values are so big. That's exactly why we're given a modulus value, and we need to have a basic understanding of binary exponentiation because using binary exponentiation we can calculate a to the power n or a to the power x, or big numbers, okay, to the power, and doing some mod manipulation. I hope you get that. So you just need a basic binary exponentiation technique to learn. That's all actually. So basically the answer goes down to the n to the power k. That's it. That's all we care about. I hope, okay, let's take it to the code section here. There you go. Taking the T, taking the N and K, simply just expo. Inside this expo function, we are dealing with the binary exponentiation to calculate a to the power n, or here like x to the power n, I guess. I actually did it in iterative way rather than going for a recursive way. Also, if you don't know, the complexity is actually log of n of this binary exponentiation. And if you don't know, you can search on Google on it. I hope you will understand that. But I actually did that not in a recursive fashion, but in a much more of an iterative manner. I hope you get that. Finally, we're just going to be just printing the answer. That's all we care about. Okay, so I hope I made you understand that. Yeah, so till next time, goodbye.